So in this lecture, we're going to focus on conditional probability, talk about some important concepts associated with the conditional probability, the formula for it, and as well as some important ideas that are implied or entailed by it. And then we're going to use the conditional probability formula to practice solving some somewhat complex and hopefully interesting probability problems. So what is conditional probability? Well, put simply, it's the probability that something happens or is true, depending on whether we're talking about an event, then we're talking about something happening, or if we're talking about a proposition about something else, sometimes an event, then we're going to talk about, instead of what happens, we're going to talk about what is true. So it's the probability that something happens or is true on the condition that something else happens or is true. So here are some examples of statements in sort of everyday language or something close to it that are containing a statement of conditional probability. So the probability that Jed will be late for class if he failed to set his alarm. So that logical connective of an if and what comes after that, that statement, he failed to set his alarm, or if you want to think of it as an event, that's fine. This is a conditional probability statement. Or the probability that the store is open, assuming that, that's an indicator term again that we're dealing with a conditional probability claim. So the probability that the store is open, assuming that it is a holiday. Third example, the probability that you'll be attacked by a shark, given that, or on the condition that, those are both indicator terms that we're dealing with a conditional probability. So the probability that you'll be attacked by a shark, given that you are a frequent surfer. And then finally, sometimes the order can swap in the sentence, so you have to watch out for that. So given that the first card dealt without replacement from a fair deck was a king, the probability that the second card dealt will be an ace. And so we'll practice taking these English sentences and converting them into the appropriate symbols in the conditional probability formula. But for now, I just want you to get a feel for the indicator terms as you're reading something or talking to somebody that often indicate that we're dealing with a conditional probability. So what is unconditional, or what's sometimes called categorical property or probability? Well, that's the sort of the opposite, I guess, of conditional probability. So we just talked about conditional probability claims. So let's look at some unconditional or equivalently categorical probability claims. So these types of probability claims or events we can define simply as, at first, like this. We can say that an unconditional probability or categorical probability is the probability that something happens or that something is true, but we will not use terms like given that, or on the condition that, or assuming that, or if. So if we look at our original examples of conditional probability statements, if we want to convert them into or translate them into unconditional probability statements, categorical probability statements, we would I put a strike through the text that we would take out to do so. So the probability that Jed will be late for class, full stop, that's an unconditional or categorical probability statement. The probability that the store is open, again, full stop, get rid of assuming that it's a holiday. The probability that you'll be attacked by a shark, full stop, get rid of the given that you're a frequent surfer. And here we would get rid of the first half, given that the first card dealt without replacement from a fair deck was a king, get rid of that and only hold on to the probability that the second card dealt will be an ace. Okay, so let's formally define the conditional probability rule. In math symbols, it will be the probability that B, given that A, which will be equal to the probability of B and A divided by the probability of A. And anytime we are dividing the number in the denominator cannot be 0. It has to be greater than 0. Dividing by 0 is prohibited in math because the quantity you get in doing so is undefined. It's not even a number, it's completely undefined. So whatever's in the numerator or the denominator for the conditional probability rule has to be greater than 0. So in this case, it's A, the probability of A. But you could flip it around, so the probability of A given that B will be equal to the probability of A and B divided by now the probability of B. And so in this case, B needs to be greater than 0. So it's important to keep in mind that the probability of B, usually anyways, the probability of B given that A will not be equal to the probability of A given that B. Right, so this is in general, again, I'll give you an example. So for most active astronauts are men, but not all men are astronauts. In fact, the vast majority of men are not astronauts. So the probability that someone is a man, given that they are an astronaut, is really, really high, actually. But the reverse is not true. The probability that someone is an astronaut, given that they are a man, is really, really low. Okay, now let's put this conditional probability formula to use to get just a basic idea for now of how to use it before we get into solving more complex problems with the rule. So here's our first problem. Consider a fair die. We say that the outcome of a toss is odd if it falls 1, 3, or 5 face up. Those are the only odd numbers you can get by rolling a fair die. So here's our problem to solve for. Given that we rolled an odd number, what is the probability that we rolled a 3? So the question we're solving for is the probability of getting a 3 given that it's an odd number. All right, so that straight up and down bar, again, is it's a symbol for any of those conditional probability indicator terms, like on the assumption that, given that, if, and so on. So the probability of getting a 3 given that we rolled an odd number. And we know what that's going to be equal to given our formula, or our rule from earlier. It's going to be equal to the probability of rolling a 3 and an odd number divided by the probability of rolling an odd number. So the probability of rolling a 3 and an odd number is 1/6. There are 6 total possibilities. Then out of those 6, there's only one way to get an outcome that is both a 3 and an odd number. So that's our 1/6, and we're going to divide by the probability of rolling the die and the outcome being an odd number. Well, 6 total possibilities, 3 of those are odd numbers, 1, 3, and 5. So the probability of rolling an odd number is 1/2. So then we would perform simple division. 1/6 divided by 1/2 equals 1/3. So the probability of rolling a 3, given that it's an odd number, is 1/3. And we could think of that as the probability of A given that B, and then we substitute in the relevant terms for A and B. Okay, same problem, except that instead of looking for the probability of A given that B, we're going to look for the probability of B given that A. So again, consider a fair die. We're going to say that the outcome of a toss is odd if it falls 1, 3, or 5 face up. So again, given that we rolled a 3, what is the probability that we rolled an odd number? So this is actually the opposite, right? Given that we rolled a 3 instead of an odd number in the previous problem, what is the probability that we rolled an odd number? All right, so we're looking for the probability of B given that A this time. So that's going to be the probability that we rolled an odd number given that we rolled a 3. And this is not going to be the same probability as the previous problem. So to convert it, the terms further into the rule, on the right-hand side of the equal sign, it's going to be equal to the probability of rolling an odd number and rolling a 3 divided by the probability of rolling a 3. So we know that the probability of getting an odd number and a 3 is 1/6. Likewise, And the probability of rolling a 3 is also 1/6. There's only one way to roll a 3. So our solution, the probability then of rolling an odd number, given that we roll a 3, is 1. That's certain. So there are three interesting features of this conditional dice problem set. First, I want to point out to you anyway. So the first thing is that in relationship to the previous dice problem, or die problem, we can see that the probability of A given B does not equal the probability of B given that A. So the probability of A given that B was 1/3, but here the probability of B given that A is 1. All right, the second thing that's interesting about this second conditional dice or die problem is that it illustrates why it is the case that if A logically entails B, then the probability of B given A is 1, or certain in this case, as it is in this case. So in other words, since rolling a 3 logically or deductively entails that an odd number is rolled, the probability of rolling an odd number given that you roll a 3 is equal to 1. So the third interesting feature I want to point out in relation to the second actually is that the probability of B given that A is not equal to the probability of B. And so we have a case where the probability of B and A are not independent, even though A does not cause B or vice versa. This is a sort of a logical or a metaphysical, logically necessary or a metaphysically necessary truth instead of a causal truth. So then not all dependencies between A and B are causal, although most probably are. Okay, well this third point leads into our next topic about using conditional probability to formally define independence. So let's say something about conditional probability and its implications for defining independence. So we've already defined independence informally as the statement that A and B are independent if the truth of one doesn't change the probability of the other. But now that we have formally defined conditional probability, we can formally define independence as well. And we can define it just like this. A is independent of B if the probability of A given that B is equal to the probability of A, and the probability of A is greater than 0. So here are some statements that have the indicator terms that what's being made as a conditional probability claim, but the probability of A given that B is actually just equal to the probability of A. So here's a couple examples. The probability that you will get over your cold soon, given that you take airborne, is just equal to the probability that you will get over your cold soon. The probability that you will have a good relationship with your new roommate, given that she is a Sagittarius, is just the probability, or it's equal to the probability, that you'll have a good relationship with your new roommate. So in both cases, the probability of A given that B is just equal to the probability of A. So by contrast, the probability that you'll be a victim of gun violence, which will represent with the letter V, will represent that statement that you'll be a victim of gun violence with the letter V, given that G, you own a gun, is not equal to the probability of V that you'll be a victim of gun violence, because owning a gun does affect the probability that you will be a victim of gun violence. All right, well, our formal definitions of conditional probability and independence allow us to say something formally now about the gambler's fallacy, which we've covered before. So recall that our fallacious gambler who thought that he could learn from experience, so to speak, when he saw that a fair roulette wheel came up 12 blacks in a row, fallaciously reasoned something as follows, which we can capture now nice and succinctly, but formally, with our understanding of conditional probability now. So he reasoned that the probability of the roulette wheel coming up red on the 13th trial, given that the 12 previous trials all came up black and in a row, is greater than 1/2. So this captures, in conditional probability terms, the reasoning of our gambler. But it's fallacious if the trials are independent and he knows that they are independent, which he did. So if the trials are independent, then the probability of the fair roulette wheel coming up red on the 13th trial, given that it came up 12 blacks in a row on all the 12 previous trials, is just equal to, given our definition of independence, the probability of red on the 13th trial. And that's going to be equal to about 1/2. So for sake of simplicity, we're just going to call it that probability 1/2, even though it's slightly less, but we'll ignore that because we want to make this point. The probability of getting 12 blacks in a row and then red on the 13th trial is captured here as the probability of B, 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 and then R on the 13th trial. It's going to be, divide that by the probability of getting 12 blacks in a row. So that's going to be equal to about 1/2 to the 13th power over 1/2 to the 12th power, which is equal to about 1/2. So then using conditional probability, we just proved that the gambler's fallacy is fallacious. So notice then that this not only provides a way to prove the gambler's fallacy, but the conditional probability formula and our formal definition of independence. But the formula for conditional probability still preserves the fact that the probability of A given that B is equal to the probability of A when A and B are independent and A is greater than 0. So no matter how many trials you want to put in here, the result will be the same. We'll preserve independence. And I think this is a great example of that. We're dealing with 13 trials on the one hand and 12 on the other.